Today we will talk about random variables. Okay. So consider tossing a coin 3 times. Can you give me the sample space?
Will be consisting of 3 tuples.
Yes. So 3 tuples: head, tail, head, tail, head. Head, tail, head, tail, head, and tail. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now, how many heads do you have in this outcome? In the first outcome, how many heads do you have?
3 heads.
Okay. How many heads do you have in the second outcome?
2.
How many over here? Third.
Excuse me, sir?
2. How many in the fourth one?
2.
2 heads. How many heads here?
1.
1 head. 1 head.
1.
1 head.
1.
How many here? 0 heads. Okay, so it's like I have mapped the outcomes of my experiment. I have mapped the outcome of my experiment to a number. Okay, I have mapped this outcome to the number 2. I have mapped this outcome to a number 2. This outcome, number 2. I have mapped this outcome to number 1. This outcome to number 1. This outcome to number 1. This outcome to number 0. And let me call these the numbers that I have assigned. Let me call them X. So what we've done here is that we've mapped each outcome of the random experiment to a number. And this number, let's call this number X. Is X going to be random? That's my question to you guys. Is X, the value of X, is it a random value?
Yes, sir.
Why?
सर ये चेंज हो रही है ना, वेरिएबल की यही होता है, ये x की वैल्यू चेंज हो रही है 3, 2, 1, 0.
Well, days of the week also change. It's Sunday, then Monday, then Tuesday.
Because sir, when we're gonna toss the coin, we don't know which side is gonna come up, like, you know. So it's random.
Okay, so yes, X is random. So there are 2 things here that X is. Number 1, X is a variable. Because the value of X varies, it changes. So X is a variable. Sometimes it's 3, sometimes it's 2, sometimes it's 1, sometimes it's 0. And the second thing is that it's a random variable. That these values that X gets, they are based on a random experiment. It could be 3 or it could be 2 or 1 or 0. In no particular order. You do the experiment once, maybe you get 2. You do the experiment again, maybe you get 1. You do the experiment again, maybe you get 2 again. So the values that X takes, they appear randomly. So X is a random variable. Okay. And specifically, X represents a real valued mapping or function. You can call it a function as well. Okay. For example, the function x, when you input when you input this event in the function x, it outputs 3. Okay, so it's a function that takes in events or a single event, and for each event it outputs a real number. Okay, in this case we assigned 3. I could have assigned 3.68, for example. So any real number can be assigned. So that's what a random variable is. Why should we be interested in random numbers, in random variables? If I tell you that for every head you get 100 rupees, for every head you get 100 rupees, how many rupees will you win if the first outcome occurs? Head, head, head.
300.
300. How many rupees will you win if the second outcome occurs?
200.
Okay. One hundred, 0 rupees. This new mapping is also a random variable. Let's call it random variable y. Now what if I tell you that you win 100 rupees for every head, but you lose 50 rupees for every tail? How many rupees will you win for the first outcome?
300.
300.
Second outcome?
150.
So 2 heads is 200, 1 tail is minus 50, so 150. Third event?
150.
Fourth event?
150.
150.
50 rupees.
So you win 100, and then how many do you lose?
0.
0 rupees, 0 rupees, 0 rupees, and here
minus 50.
Minus 150.
minus 150.
Minus 150.
Minus 150, 3 times. Let's call this a random variable. That's a random variable as well. Let's call it z. Okay. So for the same sample space, for the same random experiment, if you're playing, you could have many random variables. Okay. If you're playing the second game, if you're playing the game where you win 100 rupees for every head, random variable y is what you're interested in. And if you're playing the game where for every head you win 100 rupees and for every tail you lose 50 rupees, then you're interested in random variable z. Right? And notice now you won't be as interested in what was the actual outcome. 3 heads, 2 heads, tail, head. You're more interested in how much money are you making or you're losing. So that's why random variables are important. Okay. So this was the first view of a random variable, that the random variable represents a mapping or a function from events to numbers. Let's take another view. Can you describe this set for me. What is this set?
3 tails.
Yes, x will take the value 0 whenever you get the outcomes within this set. Can you describe this set? When will x take the value 1?
Head, tail, 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 head, tail, and tail, tail, head.
So you have these three: head, tail, tail. X will take the value 1 if this outcome occurs, or if this outcome occurs, or if this outcome occurs. These three. Okay, let's keep going. What is this set?
Head, head, tail, head, tail, head, tail, head.
And what about this one?
Triple heads.
This set only contains one outcome, one element, and that is head, head, head. Okay. Now, consider these sets in the green rectangle. If I take their union, do I get the sample space?
Yes, sir.
Okay,
Yes, sir.
great. So, so when I take their union, I get the sample space. And are these sets overlapping? Do they have any intersection?
No, sir.
So this means that these sets form a partition of S. And what do I mean by partition? It means that that I have non-overlapping subsets of S, number one. Number two, they completely cover S, right? Technical way of saying this is that union of those subsets gives S. Okay, and if we, in terms of a Venn diagram, let's say I have this is set A, so this is the whole sample space. This is set A. Let's say this is set B. This is set C, and this is set D. Now, A union B union C union D gives you S, the sample space, and they have no intersection. So this is a partition. This is a partition of S. It covers S. But I don't know. If this is A and this whole thing is B, okay? This whole thing is B, and this is C. Now A and B have some intersection, they have some overlap, even though their union covers S, but these are overlapping sets. So this is not a partition. Is that clear?
Yes, sir.
Okay, great. So what does a random variable do? When the random variable takes on value 0, when x takes 0, when x takes value 1, when x takes value 2, when x takes value 3, it corresponds to subsets of the sample space. And these subsets are non-intersecting, non-overlapping, and their union gives you the whole sample space, which means that the second way of looking at a random variable is that a random variable partitions the sample space. Okay, a random variable results in a partition of the sample space. Okay, let's keep going. If I tell you that the probability of heads on one coin toss is P, then what is the probability of this outcome? Tail, tail, tail. What's the probability? Anyone?
1 minus p cube.
Yes, 1 minus p cube. Tail and tail and tail. Okay. What is the probability of the event x equals 1?
P into 1 minus p square.
So there is one head p and two tails, 1 minus p square. But you can get this in different ways, in mutually exclusive different ways. So what's the probability? This is the probability of one way of getting one head. But there are many ways of getting one head, and they are mutually exclusive.
3 combination 3, sir.
Why 3? A straightforward answer is that there are 3 mutually exclusive ways of getting one head. And for each way, the probability is p into 1 minus p square. Because of mutual exclusivity, you will add the 3 probabilities. So you get 3 here. Right? Another way of looking at it is, how many ways can you get one head in 3 tosses? Well, you want to place from 3 places. How many ways can you choose one place? So that's 3C1, which is also 3. We covered this in the last lecture, binomial probabilities. Well, what is the probability of getting 2 heads?
P square into 1 minus p.
Wrong. What's the right answer?
3 combination 2 bhi aayega, sir.
3 combination.
Yeah. There are, which is actually 3, right? Both of them are 3. 3 choose 1 is 3, 3 choose 2 is 3. And there are 3 ways for both values. And what's the final answer? Probability of 3 heads.
Sir, p cube. P cube.
And how many different ways?
P3. 3C3, sorry.
Which is 1, right? There is only one way. Okay. But for completeness, let's write 3C3. In how many ways can you pick 3 places from 3 places? Well, that's only one way. And for completeness, let's write this in the same format as well. How many ways can you pick no places from 3 places? There's only one way, because I don't want to place a head. Okay, which means I only want to place tail, tail, tail. Well, there's only one way of doing that. Okay, so let's look at these probabilities as well. So when we look at these probabilities, what do we get? Wrong pen, I'm sorry. Okay. Can we make a table which has values of x, and the values that x takes are 0, 1, 2, and 3. So in the first row you have the values of x, and in the second row you have probabilities. Okay. So what is the probability that x takes the value 0? You just computed this. What is the probability that x takes the value 0? Quickly.
One minus p cube.
Yes, 1 minus p cube. What is the probability that it takes value 1? 3p 1 minus p square. Okay. What is the probability that it takes value 2? That's again 3 p square 1 minus p. And the probability that it takes the value 3 is just p cube. Okay. Okay, so this gives me a table. Great. This table, and this is the third way of looking at a random variable, is that this table is called the probability density function of my random variable. In this case, my random variable is x. It is also called, because you'll see these terms in some books, so it's good to know all the names of this table. It is also called the probability mass function. Of x. It is also called the probability distribution of x. Okay, so it has a lot of names, but the most common name or the name that we'll be using in this course is density of the random variable. Okay, it's just the values of the random variable and the probability. Okay. Okay. The good thing about this is that this density can be computed using using the rules of probability. Okay, you do not need to perform the experiment. See, the experiment that the example that we're using over here, it has only 3 coin tosses. What if you had 300 coin tosses or 3,000 coin tosses or 1 million coin tosses? You could still come up with the density, the table, the probability density function. You could still come up with this table based on the rules of probability without tossing a single coin. Right? So that's the benefit of computing these density functions. You don't need to perform the experiment. You have the probabilities with you. Okay.
Excuse me, sir.
Yeah.
सर ये जो टेबल है राइट साइड पे प्रोबेबिलिटी और 0 वाली जो है कॉलम उसमें 1 माइनस पी का स्क्वायर क्यूब नहीं होना चाहिए?
Yes, it should be cube. My bad. Thank you. It should be cube. Okay. Okay, so that's a density function. Now let's take a small detour and discuss types of random variables. Types of random variables. Okay. In fact, let me do this. Let me do this here. Random variables, you can have a broad division of random variables is you can have discrete random variables and you can have continuous random variables. Okay. How do you define a discrete random variable? A discrete random variable partitions the sample space S into countably many subsets. In fact, let's not say subsets, even though they are subsets, but into countably many disjoint events, because it's a partition, so the events should be disjoint. And when we say countably many, this can contain 2 categories. Either the disjoint events are finite, or if they are infinite, then they are at least countably infinite. Let me give you an example. In fact, you've been studying these examples from day one. Coin toss. Any random variable based on a coin toss, the coin toss partitions the sample space into head and tail. Okay, and any random variable based on this partition will also partition the sample space into these two disjoint events. Die roll. It partitions the sample space into disjoint events: 1, event 2, event 3, event 4, event 5, event 6. These are finite. These are finite sets. Okay. And so these are discrete random variables. And for discrete random variables, you can write the density function. You can have the value of x, and you can have the probability of that value. Let's say x takes on value a1, x can take on value a2, and let's say an, and let's just assume that it has infinite values, but they are countably infinite. Okay, and let's call the probability the probability of x equals a1, let's call it p1. Probability that random variable x takes on value a2, let's call it p2, and so on. That's a density function of random variable x.
सर ये ना कि पॉइंट्स में आंसर नहीं आएगा, पॉजिटिव इंटीजर्स में सिंपल आंसर आएगा.
No, that's not true. Let's have another die roll. Let's give an example. I have a special die. And the numbers on that die are 1.1, 2.1, 3.1, 4.1, 5.1, and 6.1. Now your answer is not in integers, right?
Yes, sir.
But is it finite?
Yes, sir.
So which means it's a discrete random variable. As long as it's finite, or if you can count on it, if it's countably infinite, that's a discrete random variable. Okay? And you can have these density functions for discrete random variables. Okay. And the density function or discrete random variable has the following properties. Property 1, any pi, because it's a probability, it must be greater than or equal to 0 for all I. This symbol, are you familiar with this symbol for all?
Yes,
Yes,
sir.
sir.
Yes.
For all I. Okay. And the second property is that since it's a partition, the sum of these probabilities, p1 plus p2 plus ... what will this sum be?
S.
The union of a1, a2, an, that will be S.
It will be 1.
Yes, the sum of these probabilities will be 1. So these are the two properties that a discrete random variable has. But did you notice I never said probability should be less than 1? I never said that. Why? Shouldn't probability be less than 1? Pi should be less than 1 or less than equal to 1. Why don't I put this in my properties? Anyone? Because property 1, and property 2, when combined, they imply that pi is less than or equal to 1 for all I. Why is this true? Now, P1 and P2 and all of these numbers, P1, P2, P3, all of them, according to property 1, they are all positive numbers. Yes?
Yes,
None of them is negative. None of them is negative. Okay. Now, if none of them is negative and the sum is 1, can any one of them be more than 1? If the sum is 1 and all of these numbers are positive, can any one number be greater than 1?
No, sir.
No, because then the sum would be greater than 1. And I can't have negative numbers that can bring the sum back to 1. So properties 1 and 2 combined, they are enough. They imply automatically that pi will be less than 1. If you want to explicitly write that pi will be less than or equal to 1, you can write it, but you don't really need it. First two are sufficient. So that's one thing, and we can note that for any subset of the sample space, for any subset A of the sample space, we can now write probability that the random variable takes on values in that subset. We can write this as the sum of the probabilities, where the A belongs to this set, and probability of X equals A. You're just adding up the probabilities of the events that of the elements that make up the set A. Okay, it's the sum of the probability. And this notation that we've used here, whenever we say probability of X equals A, this in capital letters, in uppercase, we refer to the random variable. That's the random variable. And lowercase denotes value taken by a random variable. Okay. So this was discrete random variables. There is another type of random variables which is called continuous.
सर ये डिस्क्रीट की एग्जांपल भी अगर आप दे देते।
मैंने दी है, हेड टेल।
सर वो पार्टीशन बना के तो अगर आप देते
मैंने दी है this is the partition. Head is one event, tail is another event, and the sample space only consists of head and tail when you toss one coin. Die roll, you could have 6 different subsets, 6 events, and the union of these events is the sample space, and they're finite. Maybe you will understand discrete random variables better when we look at continuous random variables. So please bear with me. A continuous random variable partitions S into uncountably infinite sets. Okay. Example. Randomly selecting a number between 0 and 1. Now, how many subsets can you have between 0 and 1?
So, infinite.
Like you can't have a countable number of subsets of S. Okay, it's uncountably infinite. And in later lectures we're going to cover continuous random variables in detail. Okay, but for now, let me just quickly mention the properties that a continuous random variable will have. A discrete random variable has two properties: that each probability is greater than or equal to 0, and the sum of probabilities is 1. Similarly, now you have two properties over here as well, but we are going to avoid using the term probability now. Okay, we will say that if the random variable takes on any value x, we're not going to say probability of x, we're just going to use a function f of x, and we're going to say that this function f of x is going to be greater than or equal to 0. Okay, for all x, for all values x that the random variable takes. And with discrete random variables, you could sum up the probabilities because you had countably many subsets, so you could sum each of those probabilities. But when you have uncountably infinite values, you cannot sum, but you can integrate. Okay, and so if you integrate these values of this function from minus infinity to infinity, right? I'm just integrating all values. The result of this integral should be 1. Okay, and in this,
माइनस इंफिनिटी में क्यों गए हैं? हमें तो 0 से 1 तक चाहिए.
oh, so can your random variable be less than 0 in this case?
नहीं सर.
Well, then f of x will be equal to 0 when x is less than 0. So I'm saying let me integrate, but wherever the function is 0, the integral will not be affected. If f of x is 0, will it add something to the integral? Look, we're going to cover continuous random variables in detail later. I'm just doing this for completeness. This function f of x is called, once again, the density function. Okay, and you should note the difference. for discrete random variables, density function is the probability, but for continuous random variables, this density function f of x is not the probability. Okay, we'll come to this in subsequent lectures, but this is a very, very, very important point, and I want you to remember this. Okay. Okay. Now, and this whole lecture is only for discrete random variables. Today's lecture only covers discrete random variables. There is a fourth way of looking at a random variable. We've done 3 so far. There is a fourth way of looking at a random variable. Now, let me copy this density function . So this is my density function for the number of heads when I toss a coin 3 times. Okay. Now assume that the coin was fair. So the probability of heads is half. Okay. Then what probabilities will you get? Can you give me the probabilities of the random variable when p is half? Anyone? What do you get here for 0?
So 1 minus p by 2 whole cube.
And what's the answer?
1/8.
Okay. So let's draw these probabilities. Yeah, the answer is 1/8. So so when x is 0, when x is 1, when x is 2, and when x is 3, for 0 you get 1/8. 1/8. For the probability of 1 head is what? This will be 3/8. This will also be 3/8. And this will again be 1/8 if the coin is fair. Okay, so that's 1/8. This is going to be 3/8. This is again going to be 3/8. Are you guys following this or are you lost?
Yes, sir.
Okay, and this is going to be 1/8. Okay, so I have just redrawn the density function as a stem plot. So every value I draw a stem. It's like a small tree or a stem growing up. So I've drawn it as a stem plot. Okay, great. Now let me draw another plot which again takes the values so you have 0, x equals 1, x equals 2, x equals 3, and what I'm going to draw now is this probability that random variable x is less than or equal to, let's say, some value t. It could be any value t. Okay. When t equals 0, okay, when t equals 0, what is the value of probability of x is less than or equal to t? And let me define this as a function. Capital F of t equals the probability that random variable x takes on value t or less than t. Let's do this here. Can you find for me probability of x less than 0? What is the probability that x will be less than 0? Anyone? Use common sense, please.
0.
Less than 1/8.
What is your random variable x? What does it represent? What values does it take?
0 over 0.
0 over 0. Do you see the values of x on the screen? The possible values of x on the screen, do you see them?
Yes, sir.
What are the possible values of x?
So 0, 1, 2, 3.
Okay, now can you answer this question for me? Probability of x less than 0?
So 0.
Yes, x cannot be less than 0. X can only be either 0 or 1 or 2 or 3. So you're asking me to compute the probability of a set that is empty. Right? X less than 0 is an empty set. It never happens. There is nothing in this set. And the probability of an empty set, axioms of probability, that's 0. Now can you answer this question for me? It's less than or equal to 0. How do I find this? What is this? Quickly.
सर इसमें तो एक ही है ना 1/8 होगा.
Does it contain only one element or many elements?
Sir, only one element.
Isn't it equal to probability of x less than 0 plus probability of x equal to 0?
Yes, sir.
Right? And what is probability of x less than 0?
0.
And what is probability of x equal to 0?
1/8.
1/8. And so the answer is 1 by 8. Okay. And this thing is actually capital F of 0, right? Because we defined this function f of t is the probability that the random variable is less than or equal to t. Do you follow this? Do you follow this? So now I'm going to plot the function f for t equals 0. Over here the answer is 1 over 8. And what was the answer for f of t for t less than 0? What was the answer when you were less than 0?
0.
0. Exactly. For all values of t less than 0, this function was at 0. Okay. So I'm just drawing it over here for visualization, but you should understand that this line is exactly on 0. Okay. Just for visualization. And I use this notation that the value of the function at 0 is this black dot, not this empty circle. The value at 0 is this filled circle, which is 1 over 8. Okay, let's continue. What should be the value of this probability of x less than 1? Can I write this as probability of x less than 0 plus probability of 0 is less than equal to x is less than, not less than equal to, less than 1. Can I write it like this?
Yes, sir.
Okay. What is this?
0.
And what is this?
So 1 by 8.
Yes, this is equal to probability that x takes on the value 0. Because look, x cannot be between 0 and 1. It's either 0 or it's 1. And you're saying I want the probability that x is greater than or equal to 0 but less than 1. Well, if x is less than 1, it can only be 0. Okay, so this probability is only equal to the probability of x equals 0. And so what you get is 0 plus the probability of x equals 0, which is 1 over 8. And it's still 1 over 8. Okay. Can you find the probability of x less than or equal to 1? Can you guys now lead? What should I write? Plus probability of, what should I write here?
So x equals to 1.
X equals 1. This thing here we just saw, this is 1 over 8. And what is this?
Three over 8.
3 over
3
8.
by 8.
3 by 8, great. So the answer is 4 over 8. Okay, let's keep going. Which means that when I reach 1, the answer should be 4 over 8. But as long as I am between 0 and 1, as long as I am less than 1, okay, between 0 and 1, the probability is going to remain 1 over 8. Okay. But as soon as I reach 1, the probability is going to jump to 4 over 8. Okay. So the empty circle means at 1 the value is not this one, the value is the filled circle. Okay. And using the same logic, the probability is going to remain the same, and then at 2 it will jump to which value? Anyone?
So
7 over 8.
3 over 8.
4 over 8 plus 3 over 8, which is 7 over 8. And then it's going to remain at 7 over 8 until 3, where it's going to jump to what? Anyone?
1, 8 by 8.
8 over 8, which is 1, yes. And what about greater than 3? Like, will the probability now remain at 1? Forever? Yes, it will remain at 1 forever.
1.
Because your random variable, whatever happens, your random variable is going to be less than equal to 3. 100% chance your random variable is going to be less than equal to 3. 100% chance, which means probability 1. Okay. Now this function that I've drawn, this complicated looking function, this is called, because we were adding probabilities, this is called a cumulative. You're accumulating these probabilities, you're adding probabilities. It's called a cumulative distribution function. That's the fourth view of random variable, that with a random variable you also have a cumulative distribution function which is just this function f of t equals the probability that the random variable takes values t or less than t. So it's a sum of all the probabilities of the random variable less than equal to t, and t can be any real number, okay. So let me encircle this just to show you that this is important. This is the cumulative distribution function. Okay. Now, and here's the important part. Can you give me the value of, oh, by the way, this here was the density function. On the left was the density function, probability density function. Okay, and what we did here, it gave you the cumulative density function. Okay, cumulative distribution function. Okay, let me write it in full. Probability density function and cumulative distribution function. And did you notice that the CDF, we arrived at the CDF by using the probability density values? 1 over 8, 3 over 8, plus 3 over 8, plus 1 over 8, right? We added the probability density values to get the cumulative density function. And therefore we can go back as well. So for example, can you tell me what this value is? When I say 0 superscript minus, it just says values less than 0. What's the answer for this? Because see, there is a jump at f of 0. So what is f of 0 minus f of 0 minus?
One over 8.
Yes, this is 1 over 8 minus 0, which is 1 over 8. Okay. What is f of 1 minus f of 1 minus? What is f of 1? Capital F of 1.
3 by 8.
No, look at the CDF. Look at this function, this staircase. ये जो सीढ़ियां सी बनी हुई है. 4 over 8. Yeah. And what is the value of f for values less than 1?
1 over 8.
This is 1 over 8. Yes, 1 over 8. And so you get 3 over 8. Okay. What is capital F of 2 minus capital F of 2 minus?
Seven over 8 minus 4 over 8.
7 over 8 minus 4 over 8, which is 3 over 8. What is f of 3 minus f of 3 minus?
One minus 7 over 8.
Yes, 1 minus 7 over 8, which is 1 over 8. Do you notice the numbers on the right? Do they look familiar? These numbers on the right? Do they look familiar?
सर ये वही वैल्यूज हैं जो हम लोगों ने p को 1 over 2 एज्यूम किया था तो फिर निकाली थी.
So which means that while it means that adding of probability density values gave you the cumulative distribution function, while subtracting, the inverse of adding, right? You were subtracting the cumulative distribution function values, you subtracted them, and they gave you the PDF. Okay, so you start with CDF and you subtract, it gives you the PDF. And if you start with the PDF and you add, it gives you the CDF. So there is a link, there is a relationship between the probability density function and the cumulative distribution function. And these jumps that you have over here, for example, this jump is 1 over 8, which is the probability density value. This jump is 3 over 8, which was the probability distribution, probability density value. This was again 3 over 8. This was again 1 over 8. So the cumulative distribution function holds within it, it's hidden, hides within it the probability density function as well. So you could go from the probability density function to the cumulative one, and you could return back from the cumulative to the probability density functions. And this, I don't know if this appeals to you right now. It might be hard to understand right now why this should be important, but hopefully in later lectures you will see the connection or the importance of this connection. But for now, let me just summarize this, that from density you add and you go to the cumulative distribution function, and from the cumulative distribution function you subtract and you go to the density. And the way that we've the way that we have defined the cumulative distribution function, you have some properties. So the cumulative density function has some properties. The first property is that the cumulative density function, capital F of t, is a non-decreasing function of t. Do you guys know what this means? Can anyone explain? CDF is a non-decreasing function of t. Remember, this here is the axis for t. Values of t are increasing in this direction. Okay. The cumulative density function is a non-decreasing function of t. Can anyone explain?
सर जैसे जैसे t की वैल्यू इंक्रीज होती है 0 से 3, तो f ऑफ t क्यूमुलेटिव डेंसिटी फंक्शन वो इंक्रीज होती है उसकी वैल्यू, और 3 के बाद वो 1 ही रहती है, ना इंक्रीज होती है ना डिक्रीज होती है, तो उससे नॉन डिक्रीजिंग फंक्शन है.
Yes, but does it increase all the time? Like, is it always increasing? So for example,
No, sir.
yeah, between 1 and 2 it is not increasing, it's constant. But it's not decreasing. That is important. Whenever it will change, it will increase, but it will never go down. It can remain the same for some time, but it will always increase eventually. Okay. So this is what a non-decreasing function of t. And it is a non-decreasing function because we are adding positive numbers all the time. Whenever you're adding only positive numbers, your function is only going to increase, or it can remain the same, but it's never gonna decrease. Okay, so CDF is a non-decreasing function of t. That's the first property, which is quite obvious. A second property is that f of minus infinity equals 0. and f of infinity equals 1. Now I am tempted to not explain them and say that they are obvious. Are they obvious to you? They should be obvious to you. Are they? So translate this. Use the formula. F of infinity means probability that x is less than equal to infinity. Well, the random variable is going to take some value, right? All possible values of the random variable are going to be less than equal to infinity, right? And if you want to and this is the sum of all of them, that sum will definitely be 1, because this set contains all possible values of the random variable. Similarly here, this means probability that x is less than equal to minus infinity. Well, your random variable, the range of a random variable, the range of any random variable is always between minus infinity and infinity. Even with this example that we had, x took on values 0, 1, 2 and 3. Well, aren't these values, all of them, aren't they between minus infinity and infinity? Right?
Yes, sir.
So all possible values of a random variable are going to be less than infinity, which means that the sum of all of those values is going to be 1. And no value of the random variable can be less than minus infinity, which means that the probability of going even lower than minus infinity, that's 0. So these should be obvious. Okay. The third property. This requires a little bit of calculus. Is everyone studying pre-calculus right now, or only the students that have the medical background?
Only the medical students.
Okay, so you guys are not studying calculus in this semester. That's unfortunate.
No.
Okay. Okay. Well, f of t is right continuous. What it means is that whenever you had a jump, then you chose the value that if you came from the right side, you would have reached this value. But if you came from the left side, then you would have reached this value. And so because we're choosing the value that you reach when coming from the right, that's why we say that this function is right continuous. Okay, when you're coming from the left, you notice a sudden jump. Okay, so but you'll study this continuity and all that in calculus, so let's leave it for now. And the most important part, the link between density and CDF, cumulative distribution function. The probability that random variable x takes on the value a equals CDF at a minus CDF at a minus. This is exactly what we had here. Because this thing that you had over here, wasn't it probability of x equals 0? And wasn't this probability of x equals 1? And notice what you had here, capital F of 0 minus capital F of 0 minus. You had CDF of 1 minus CDF of 1 minus gives you probability of x equals 1. CDF of 2 minus CDF of F2 minus CDF of 2 minus gives you probability of X equals 2, and similarly. Okay, this was a very, very important property. Okay.